Okay, so let's start electromagnetic induction. Electromagnetic induction or EMI. Okay, so first thing here is that what is electromagnetic induction and what are the concepts related with that. So in general, first we should have a general idea that electromagnetic induction means there is a generation of electromagnetic, that means not force, but generally we say EMF means electromagnetic force, but it is actually the potential difference, or you can say we create electric field, right, in some coils. How do we do that? So for that we need to first discuss about the Faraday's experiment. So there are three experiments done by Faraday, so that we will discuss, then we'll go into details. So Faraday's experiments. So first experiment one, what happens is that there is a coil. It is considered that there are, this is a circular coil and it can have many number of turns in that, and it is connected with a galvanometer. Okay, one. So what happens is that there is a galvanometer here, and this galvanometer should be able to detect if any current is passing through this coil or not, and we are using a magnet. So there is a magnet which has north pole and south pole. Okay, so this magnet is moving relative to this coil. You can move this magnet towards the coil, or you can move it away from the coil, or you can keep the magnet stationary and move the coil towards or away. So this relative motion should be there. So when there is relative motion between a coil and a magnet, then there will be current produced. How do we know current produced? Because there will be deflection in the galvanometer, right? So this is the first experiment. Now from this experiment some observations are there. The observation is like, if you move it with high speed or low speed, then there can be more deflection or less deflection. That means the relative motion directly affects the current or the deflection in this galvanometer. Okay, so we can note that this um, relative relative motion if relative motion is high, then current current will also be high. Okay, so this is about the magnitude. That means more relative motion, more current; less relative motion, less current. And also direction is important. If the direction is different, then current direction also changes. So direction of relative motion changes. So current direction will also change. Current direction changes. So these two things have been also observed. Then there can be other factors, like if there are more number of coils, then there will be also more current, and less number of coils, less current. All these observations were there, but this is the major observation, that relative motion is there, and because of relative motion current is produced. Second experiment number 2. In experiment number 2, what happened is that instead of a magnet, Faraday replaced the magnet with a coil, because at that time people knew that current carrying wire also behave like a magnet. So he replaced the magnet with a current carrying coil. So let us say that he has put some coil here instead of magnet. This is like a coil. This also may have many number of turns, and here some battery will be there, some battery is connected here. So because of this battery connected, there is a current is flowing in this, some current is flowing here, right? And Now this current carrying coil is there, and the first coil in which we want to check whether current is there or not, this is of course connected with a galvanometer. Okay, so if you are moving this, if you are if you are moving this, now here also we have to move. So which is easy to move? I think the coil is easy to move, because there is battery connected. It will be difficult to move the whole entire setup. So you may move this, but anyway, if it is possible to move this, you can move that. So again here relative motion is important. If there is relative motion, again if there is relative motion between these two coil, one coil is current carrying coil, another is not having any current, but in that second coil current is being produced because of relative motion. Okay, so that was the second experiment. Here also he observed a similar effect, but here observation was that if you make this current flow in one direction, the induced current will be in one particular direction. If you change the direction of current, then direction of current induced will also change. Other observations were similar. If you are moving this way, then one direction. If you are moving away, deflection direction will change. So all these observations were there, but here also relative motion was there. So Faraday was thinking how to produce current without moving anything. Without moving anything, can we produce current or not? Then in the third experiment, he modified little bit in this, and he could do that. So what was the modification? The modification was, there was a switch now. So in this coil, current carrying coil, we are now putting a switch. This is battery and there is a switch now, like this. Okay. So this switch, let us say switch is S, and this is battery. So now right now let us say current is not there and coil is also nearby. This coil in which you want to see, this is also connected with a galvanometer and it is kept nearby. Now what happens is that you are going to switch on. Okay, this you are going to switch on. This I will just correct it. This should not touch, of course. No. Okay, so here you just switch on. So when it was switched on, and there was no relative motion there, it was just switch on. When it was switched on, it was found that at that moment when it was switched on, there is a momentary deflection. Similarly, after that, let us say it is switched on, immediately deflection happen. After that it is switched on only, but there is no deflection afterwards. But again when this is switched off, then again deflection is there, but this time deflection is in opposite direction. So that means during switching on and off only deflection happens in this coil. Clear? Right. So during switching on and off, during switching on and off, deflection happens. Deflection in galvanometer happen. Now, after doing all these experiment, what did Faraday concluded? He concluded that there must be something which is changing inside the coil. Because of the change of that thing only, there is, current is generated, or EMF or voltage difference is being produced. Because without voltage difference, current cannot be there. So that's why he gave his law. So what is the Faraday's law? We will see that Faraday's law. So Faraday's law of EMI, electromagnetic induction. So the Faraday law is, say that, let us say that there is a coil, and in this coil, suppose some magnet is there nearby, north, south, or there may be some magnetic field passing through the coil, because magnet will produce magnetic field, and this magnetic field will be passing through this coil, right? This magnet is producing magnetic field, and that magnetic field is linking through the coil. So there is a term called magnetic flux, magnetic flux, which is similar to electric flux, and it is represented by phi b. Phi b is B dot area vector. Okay, so if there is a coil and there are magnetic field lines cutting it, then there will be magnetic flux through the coil. And if the magnetic flux changes through the coil, then only there will be EMF induced in the coil. And if there is EMF induced in the coil, then there can be current in the coil. Okay, so that is what it is. So EMF induced, EMF induced is given as minus rate of change of magnetic flux in the coil. Negative rate of change. Now negative sign has got importance here. This negative sign has got importance. What is the importance of this negative sign? Means it will try to oppose the change, or it will produce a current in such a manner that it will oppose the cause. So the effect is such that it will oppose the cause, so that that should stop. Okay, so let us try to understand with example. Suppose you are moving this towards this side. Let us say you are moving it towards. So what happens if you are moving this magnet towards? So right now this magnet is creating magnetic field, and this magnetic field which you can see here right now, this magnetic field, let us call this as external magnetic field. External means this is the magnetic field produced due to that magnet which is, moving. So this external magnetic field is increasing in this direction because magnet here moving closer. So in this direction magnetic field will increase, and because of that flux will increase. Correct, flux will increase. Now this coil must try to produce current in such a manner that it should try to decrease the flux in this direction. So to decrease this flux, this coil must produce a magnetic field in opposite direction. So this must produce a magnetic field in this direction. This is the magnetic field induced. Okay, magnetic field induced means this current, this coil must produce magnetic field in opposite direction. But how can it produce? For producing magnetic field, it must produce current inside that. Okay, so that is why this coil must produce current, so that this is how it should produce. That current should produce this field. Induced current will produce this induced magnetic field, which will oppose this external magnetic field. Now suppose if I am seeing, let us say I am this side, and this external field I am looking now coming towards me. So the induced magnetic field should go away from me. So induced magnetic field going away means from this direction it should be clockwise. So from right side when I am looking, the coil should have a current of clockwise. Clear? Right, so that's how we can decide the direction of current. So current which will be produced in this must be in this manner, clockwise current, clockwise. And in the same way you can explain this concept. Then there is a negative sign can also be explained by Lenz law. Lenz law explains this based on energy conservation. How energy conservation? Let us try to understand the same thing. Suppose if you are trying to move this magnet, now let us say that instead of magnetic field induced in this way, let us say magnetic field is this way, or let us say the current produced is anti-clockwise. That means more and more magnetic field will be coming this side, and that magnetic field will apply force on the magnet, and the magnet will accelerate. And if the magnet accelerate, magnet kinetic energy will increase, right? So that means energy is increasing. First of all, current you are assuming as anti-clockwise. That anti-clockwise current will produce magnetic field in this direction. That magnetic field will accelerate that one. That means there are two things happening. One is that current is produced, another is kinetic energy in the magnet is produced. So in both way you can say energy is produced. But how can energy be produced in both ways? If one place energy is produced, another place energy should be consumed. Then only energy conservation idea you can apply. So using this idea, Lenz gave the concept that if it is moving like in this way, then clockwise current should produce, which should oppose the motion of the magnet. Okay, it should oppose the motion of the magnet, so that the work done in moving the magnet converts into electrical energy in the coil. So that is what is Lenz law. Lenz law explains that. So Lenz law can be very easily summarized like this. Can be summarized like this. Suppose if this is a current carrying coil, and let us say if you are moving in, let us say you are moving in north pole towards this, then it will be developing like this way. You can remember it. So if you are pushing the north pole in this coil, then magnetic field is increasing in this direction. So in order to oppose that, it will induce magnetic field in opposite coming out. That magnetic field means current must be anti-clockwise. So this arrow represents anti-clockwise current develop in this coil when you are pushing the north pole towards the coil. Similarly, south pole, suppose you are moving the south pole, then suppose you are moving south pole means magnetic field which is coming in this way, because towards the south pole magnetic field comes. So magnetic field will be coming out, that magnetic field will increase. So to oppose this, it will induce magnetic field going inside. Going inside means current must be clockwise. Clear? So this is the idea about that Faraday's law and Lenz law. Then lot of concepts are there in this, and basically all the concept can be classified into three things. So idea is that you have to develop current. So first thing is that how will you change the magnetic flux? So to change magnetic flux, you can change the magnetic field, change magnetic field. Second concept can be um, change the area itself, change the area. And third concept is change the angle theta, change change this angle. Okay, this is area that you have to change, and this angle that also you have to change. What is this angle? Let us understand that. Suppose if this is magnetic field, okay, this is magnetic field, external magnetic field, and this is a coil. Coil may have a number of turns, and the perpendicular to this coil, this is what is area vector. This is area vector perpendicular to the coil. Okay, and if this is perpendicular area vector, then this angle between the area vector and this magnetic field, that is what is theta, right? So if you can change any of these things, then there will be flux will change, because flux is nothing but B dot area vector, so which is B A cos theta. So if you change magnetic field, flux will change. If you change area, it will change. If you change theta, it will change, right? So many questions are based on changing the magnetic field. So let's first check that. Take some questions based on that. Suppose magnetic field in a coil is passing through that, and let us say magnetic field is perpendicular. Uh, Magnetic field is perpendicular. Okay, that means coil is like this. Area vector will be like this, and magnetic field will be like this also. Let us say magnetic field is also passing through this. Magnetic field and area vector in same direction, but the magnetic field is changing like this. Let us say 2t plus 3. One simple example. So they can ask what will be the emf induced. So emf is minus d phi b by dt. First calculate phi b. Phi b, this is magnetic flux. B dot A, here this angle is 0 between them because they are in the same direction. So it is just B into A, right? And area will be given to you. Let us say area is 1 meter square. 1 meter square. So this is just going to be B only, which is nothing but 2t plus 3. Now you differentiate that. So when you differentiate that, what do you get? You get minus this as 2, right? You get 2. So this EMF is minus 2. EMF is minus 2. 2 volt. Minus just indicate the direction. Minus will indicate the direction. Now here, how minus we can indicate here? Let's understand that. It's an important thing. How to show that. So suppose if I am showing, let us say I am showing the like this way in this plane. So when I am showing potential difference, so we need to connect a battery. So you can see that magnetic flux is increasing in upward direction. So to oppose this, it will produce downward. Downward means it should go like, if I see from the top, it must go clockwise. So this should be the current direction. Current should be like this, induced current. Now to have this induced current, you can keep a battery like this. A battery like this. We are seeing from top. From top, you are seeing this is top view. This is how a battery should be connected, and the battery has EMF magnitude. Now you can write as 2 volt. Clear? Like this we can see. Sometimes they will ask that how the current is flowing here. You can show like this way. But if you consider this, here current is flowing from negative to positive. Okay, current is flowing in, because current inside the battery goes from negative to positive, and current outside the battery go from positive to negative. There is a difference. So we need to look at when how they will ask, because in some time they may give like this point as A and this point as B. And if they ask in the wire AB, means it will go like this way, and in the wire this portion BA, it will go this way. So according to question, you need to see that, right? Okay, then what about changing of area? That is what is motional EMF. Motional EMF. And before that, let us cover this change of angle. That is nothing but AC, concept of AC. So suppose if you take this coil like this, and this is the angle, area vector, and this is magnetic field, and theta. Suppose theta is changing, or you are rotating this coil like this way, so this angle will keep on changing. So at any instant, this theta is equal to omega t, right? Theta is equal to omega t. Now, or you may say d theta by dt is equal to omega. That also, let us say that it is a constant angular velocity, you are rotating it. Then initially it was here, this coil was initially like this vertical, so angle was 0. Okay, so how do you calculate now? Flux, magnetic flux. So BA cos theta. Now EMF is equal to minus differentiation dP by dt. So differentiate this, so minus BA cos theta, differentiation becomes minus sin theta, and d theta by dt you have to write as omega. So you can write this EMF as BA, this will become omega, BA omega sin theta, correct? Like this. And suppose it has n number of turns, let us say that there are n turns are there. So you can write this EMF as n times BA omega. Sin theta can be written as sin omega t. Okay, and this is what is alternating, because you can write this as E max into sin omega t. Okay, this is the next chapter topic connecting with that. Okay, E voltage is equal to maximum voltage into sin omega t. So this is this formula will be used. So many questions are coming in every shift on this. Okay, right? Okay, then what else? 1 minute. हाँ बोलो ना. हाँ, give me 1 minute. Yeah, sure. Okay, so this is over. Then next, motional EMF. Motional EMF. So in motional EMF, what happens is that, let us say, for example, that this is a frame and there are magnetic field which are perpendicular like this, and there is a conductor. Let us say there is a conductor. This conductor you are sliding or moving over this. Okay. You are trying to move this conductor in this magnetic field which is perpendicular, and the velocity v is perpendicular to the length. This L is the length. Okay. Now as we are moving it, what is happening? Let us say that this is the distance x here. This is the distance x. So you need to consider this area, because if you take magnetic flux at any time, you will be writing b into this area, and because the area vector is also perpendicular, so the angle between area vector and the magnetic field is 0, right? So b into a, so area is nothing but L into x. Now if you calculate EMF, that will be minus d phi b by dt, so that will become minus bl dx by dt, and dx by dt is nothing but velocity, so minus bl v. Now here again the minus sign, how do we write it? So this you need to note that what is the direction of current. First you need to figure out the direction of current. So can you tell me which direction current will be there? Like for example, I am writing this point as P and this point as Q. So is the current going, uh, current is going up, right? That means in this outside it will be going like this way, right? Like this. This is the direction of current. That means here it is anti-clockwise, correct? Right. So if I say that current is going anti-clockwise and I want to draw this cell or the battery in this rod PQ, so how can I draw that? I can consider it like this way. Uh, I'll just erase this one and I will make a battery here like this way. Yes, can we do this? We can show this rod like a battery with this end as positive and this as negative. Like this we can show. So that means what? That means this is like a battery now, EMF, and this EMF value is BLV, and if you are moving it with a constant velocity, so it will have a constant battery voltage. That's what it is. Okay. Hmm. So this is what is motional EMF. Similarly, there is a concept of rotational EMF. Rotation, if you are rotating a rod, suppose for example that there is a rod like this rod is there and there is magnetic field, let us say cross cross. Now this rod, this is the midpoint too, and this point is P and this point is Q. Now let us say that you are rotating it with a constant angular velocity omega, constant angular velocity. So there will be EMF produced between the ends, or between the center and the end point there will be EMF. Also note that EMF can be produced, but whether current is there or not, will there be current in this rod or not? Hmm? See, for current, na, you need a closed circuit. Okay. But here this rod is only there. There is no closed circuit. So current will not be produced. Battery or EMF will be developed. It will be like a open cell or a open battery which is not connected with any circuit. Okay. So if it is like that, then what will happen? There will be EMF induced, but current will not be there. Okay. Previously here there was current. Why? Because this circuit was there complete. Correct. Right. Now if you try to see how to find out here, now let us see here some small element you need to choose. Let us take a small element on the small length which you can take as dx, and from the center this position is x. Okay, so you are choosing this small element on the rod. Okay, now now you want to find out what will be the small EMF develop in this. Now if you see this small element, it is right now going in this direction with some velocity v, correct? And because it is like a circular motion, because this is like a circular motion, right? So this v equal to omega r we can write. So this v is equal to omega, radius is x, so we can write omega into x. Okay, so this is small element which is moving with this velocity, there is EMF induced, and that small EMF we can just use the formula as bvl. B is the magnetic field, v is this velocity, but its length is very small, so that is dx, correct? Okay, then you just integrate it to calculate the total EMF. But now the question is from where to where you want? You want between center and P, center and P. So you have to go from x equal to 0 to x is equal to radius of this, or which is you can say as L by 2, correct? L by 2. You have to go from 0 to L by 2 because you want potential difference between center and point P. Suppose if you want potential difference between Q and P, then what will be the limit here? So 0 to how much? Total length is this length. This is O. O means this is x equal to 0. Okay. This point is nothing but x equal to 0. And this point is x equal to L by 2 plus L by 2. So what will be this then? X equal to minus L by 2, right? So if you have to go from, you want to find potential difference between Q to P, so minus L by 2 to L by 2 you have to take. Okay, let us take from 0 to that. So you calculate it. Okay, so this will come B, but V is omega x, omega come x integration x square by 2, and this you have to do from 0 to L by 2, 0 to L by 2. So that will become B omega by 2 will come out. So this will become as L square by 4 extra term. So B omega L square by 4 will come, correct? 4 into 2, 8 will become, correct? But if I take minus L by 2 to L by 2, then what it will be? Will it become 0? Hmm? It will become 0, I think, because minus L by 2 to plus L by 2 square is always positive, correct? So it will become 0. V omega L square. But suppose if I take this as radius, let us write L by 2 as radius r. So I will write this as radius. Then this will become B omega r square by 2, correct? This is the formula which we can remember. B omega r square. R is the radius which is the half of this. But suppose if you rotate about this point Q, you can rotate about point Q only, then the entire length will become radius, correct? So it depends how you are rotating. If you rotate about the end point, then b omega L square by 2, you can use that formula, correct? Okay, so this is what it is. I think most of the questions will come on this. Beside this, there is another concept of electric field which is produced and which is a non-conservative electric field, and sometimes questions are coming on that. That we will see important result it is. Non-conservative electric field. Non-conservative, non-conservative electric field. Non-conservative electric field. So suppose if there is a cross magnetic field is there, and you also assume that magnetic field is in the form of a circular region. So we have a circular region in which magnetic field is present like this cross, and the radius, this is center and this is the radius r. So magnetic field is present in a circular region, and cross means it is going inside. Now I want to find out electric field lines, how electric field lines will be. And let us say that magnetic field is changing here. Okay, this magnetic field B is changing, magnetic field changing with time, changing with time. So dB by dt is the change rate of change of magnetic field line. So magnetic field is changing within this region. Now if I consider any point, let us say I want to find out at this point, this is a point P at a small distance r. This is point is inside this region, and we want to find electric field at that point. Okay, so or let us say you keep a charge at that point P. That charge, when you keep, that charge will experience a force. So sometimes they can ask question that what will be force on that charge when you keep at that point. So let's try to understand this. So uh, what happens is that there will be a circular magnetic field will be produced here. Circular magnetic field will be, sorry, circular electric field will be produced. So you can draw like a circle. Now which direction electric field will be there, it will depend on how the magnetic field is, assume that there is a coil. Let us say that there is a coil, although coil is not there, you can consider some imaginary coil there, and magnetic field is changing in this coil. So what will be the flux, small flux you can take and try to calculate that. So for this small region, if I take magnetic flux, that magnetic flux I can write as B into area, and this area is nothing but pi r square. Okay, so I want to calculate the EMF, magnitude of EMF I will calculate. So d phi b by dt magnitude will take, so pi r square into dB by dt, right? This is the EMF produced. Okay. Now suppose if you keep any charge here, if you keep, that charge will experience a force, and due to that force it will move in a circular motion, and due to that there will be some work done. Work done is what is work done? Work done, yeah, work done, what can we write? Work done, because there will be force on this charge particle, right? So the force we can write as, Okay, let's write the work done as force into, here you need to write as distance. Why you need to write as distance? Because this force will be acting on this charged particle, and a small displacement, when you add this small displacement will give us distance, because you have to do basically integration, right? So this force is nothing but charge into field, and this total distance is 2 pi r. Total distance is 2 pi r. This is work done. Hmm. How can we relate this work done with this EMF? Because work done is also given as charge into potential difference, correct? Hmm. So this you can also write as this charge into, huh, what? You can put it, but what we want to calculate is electric field, right? This electric field. So work done, we are trying to equate work done. One calculation of work done is integration of force dot dr. So that integration is giving us force into displacement, force into this distance. That is, force is q into e into the distance of the entire circle, because it will come back, here. So then that you can write as for charge into potential difference. That is also energy. Charge into potential difference. Hmm. Yeah. So from here, what you can do, now you can charge will get cancelled. Okay. So now you got this electric field formula. So electric field into 2 pi r is equal to pi r square into dB by dt. So from here, R now get cancelled, pi get cancelled. What do we get? Electric field we got. You wanted electric field. Think about any other approach also. Maybe there is other approach also possible, but in most of the textbook they are giving this. So R into dB by dt divided by 2. Okay, R by 2 into dB by dt. This is the electric field which is produced due to changing magnetic field, dB by d. If magnetic field is not changing, then we won't have electric field produced. Okay, so that's a non-conservative. Why it is non-conservative? Why it is non-conservative? Because charge is coming back to the same point, but still work done is there. If it is a conservative field, then work done in a closed loop is zero, right? But here work done in a closed loop is not zero, so that's why we can see that. Okay, so most of the questions you can work out within these topics. Fine. Then any other doubts you have in this? Hmm. I think, yeah, tomorrow evening, yeah, tomorrow same, I think 9 o'clock or 9:30 we can have. Okay. Yeah, you sent me previously itself. I will go through that. We can discuss them. Huh? Okay then. Okay. Yeah.